let's begin. First, test. Test written parts have been graded. I'm currently working on the multiple choice Scantrons, and then I got to add them up together, which means that most likely the numbers will be made available either later tomorrow or on Saturday, well before the drop deadline on Monday. Some are good. Some people did really good. Some people did not so good. Some people did good enough. I'll have the full histogram and everything available and talk about the test on Tuesday. Once the grades are posted to Blackboard, that means you can come and pick it up. Yeah.
Drop date is Friday.
No, drop date's Monday.
They sent out
I was told.
everybody's told us.
This, like, tomorrow?
Yeah, they should have line.
No, it's not.
Got like 40
You've got that email?
Yeah. Well, if I can find the code.
Monday is when the midterms are due.
Yeah.
Yeah, it used to be, you know how they have the saying, we are Ole Miss. In the 70s and 80s, it's like, well, we are Ole Miss. It's like, ooh, different pronunciations, way different meaning. Huh? Okay, won't be wet. So, there we go. Typically, well. So what we're going to do is we're going to continue, we're going to talk about rotation. And we're going to talk about how rotation and introduce a few new words. What we have here is a circle. We can think of it like a merry-go-round on a playground, just like a disc, just a big disc that rotates about a single point. And what I'm going to do is I'm going to blow that up. Ooh. And now, if it's rotating in a counterclockwise fashion, these points on the edge have an instantaneous velocity vector. At that point, it is going straight down. At this point, it is going straight right. At that point, it is going straight up. At that point, it is going straight left. The radius is r. And there are a few things that we need to understand, that v is equal to omega r. That the linear velocity of that point is related to the product of its angular velocity and its radius. So if you had a circle and it was rotating like that, if you were at this point there, you will have a particular velocity, but if you're further out, the r is bigger, so the velocity is bigger, which kind of makes sense. The point at the middle, or towards the middle, has less distance to move around in. So in the time that it makes one orbit, that has to make the same orbit. It has further ground to travel, so it has a higher velocity. It's just, you just got to start reasoning this stuff out. This is the translation. For a given point at a radius, this at a certain angular velocity, it will have a linear velocity of v. So omega angular velocity V is linear velocity. And R is radius. Looking at this, at that picture right there, at one moment, the velocity is straight down. At the next moment, it's to the right. At the following moment, it is up, and at the top, it's to the left. Question. How is, if any, velocity changing? If at all. Is velocity changing?
I would guess he wants to like motorize or something, if he's slowing down a little
Say that first. I'm curious.
bit. I would guess that it's slowing down.
I will make a statement. It's not slowing down. It's not speeding up. It just is. It's just turning.
Okay.
It's just turning. There's no. Think of it as a frictionless environment.
Okay, so it doesn't change.
Okay. The velocity, the magnitude of the velocity doesn't change, because if it's going 5 meters to the left, over here it'll be 5 meters per second, 5 meters per second, 5 meters per second. But those arrows are not magnitudes, they're vectors. So does the vector change? Yes. Even though the magnitude is the same, the direction is different. So if you have a changing velocity, therefore you must have blank. Acceleration. If the velocity changes, you're basically saying that dv dt is non-zero, which means there is an acceleration. Because changes, there must be an acceleration. This acceleration is called radial acceleration. This radial acceleration is the direction in which the velocity vector changes. Those are my velocity vectors as they're moving around the circle. The radial acceleration is in green. A sub r always is perpendicular to V and points at the center of the disk. So this radial acceleration lets you know where this thing is aiming. Where is the velocity changing? In what direction? The relationship between radial acceleration and this linear velocity is AR equals V squared over R. That the radial acceleration is the product of it's the ratio of the velocity squared and the radius. Couple of things that we need to start thinking about if omega increases, the linear velocity must do what? It must increase. If r increases, the linear velocity must do what? It increases. For v equals omega r, v is directly proportional. It's a horrible P. Proportional to omega, and v is directly proportional to r. You increase the distance, you increase the linear velocity. You increase the angular velocity, you increase the velocity. Now, looking at this, well, the first thing we could do is we could do a unit check. Do the units make sense on A equals V squared over R? Well, V is meters per second. It's squared, so it's meters squared per second squared, and radius is measured in meters. So you're left with meters per second squared. So yes, the units do check. Now, what's interesting is if R increases, what does AR do? If you go further out on the disk, the R value increases.
It would increase by the value, it would be directly proportional to the value of R, wouldn't it?
Yes.
V is squared.
You're catching on.
So then it would just be like omega squared times R.
Okay, very good. All right. He figured it out. Everybody else, don't worry. Let me explain. When you're looking at this at face value, and this is one of those things where something like this could be on the test. You look at the face value of A sub r equals V squared over R, and you go, well, if R goes up, the denominator gets bigger, so the whole value should get smaller. Well, you need to understand that we just talked about V is dependent on R. V is omega R. So what you need to do is you need to substitute V with quantities that are more appropriate to figuring out the relationship. AR is equal to omega squared R squared over R, which means that the radial acceleration is equal to omega squared and R. Omega squared, here's an interesting question. This thing is rotating. You have a point out there that's going around in that circle. You have a point at the edge that's going around in the circle. Which one has a greater omega? Which one has the greater angular velocity?
The one on the outside?
So what you're saying is that the one on the outside makes it around the circle faster than the one on the inside. No, if one makes one orbit on the outside, you're going to make one orbit on the inside. So let's say that it rotates once every 5 seconds. So the outer edge rotates 2 pi radians per 5 seconds. The one on the inside, its omega is 2 pi divided by 5 seconds as well. Remember that when we're talking about angular velocity, we're not talking about linear velocity, we're talking about arc. Both in one rotation make 2 pi radians of arc. And you're nodding your head. Woman in second row. Do you understand? Okay, all right, you're just sitting kind of, you shook a little. All right. No one look at her, she gets embarrassed when people look at her. Now, so this explains why when you actually move further away from the center, your radial acceleration increases. Now, one of the things that we'll talk about is I'm not even going to write it down, I'm just going to say it out loud. When you're moving around in a circular motion, you feel something. Actually, when back before Katrina wiped everything out, there used to be a Six Flags in New Orleans, right on the Lake Pontchartrain. Katrina basically just sank it. But they had something that they call the Gravitron. And if you've been at like a amusement park, county fair, they've got the Gravitron. The Gravitron is a cruel joke. You get in, it's a disc with a radius of about like 15 feet. So it's about 30, 40 feet across. And you walk in, it's basically a circular room. There's a padded wall all the way around this thing. You walk in, you stand up next to the wall, they strap you in, and then they start slowly turning. And what is the thing that you start feeling? You start feeling a gravity, a force that you think is pushing you back into the wall. And then once it spins up and you really feel like you're just leaning up against the wall, it does this cruel joke where instead of spinning like this, it goes vertical and starts spinning like that. And that is a frightening experience, because if it weren't for those straps, you'd be like, I'm dead. I'm just gonna die. What you're feeling is what they call a pseudo force. A fake force, a fictitious force. It's a force that isn't real. But one of the things that we need to talk about, just to introduce it, just for the depth of knowledge, is let's say the room, all the windows were blacked out, you couldn't see outside. We know that there's a planet beneath us, and that planet has gravity and it's pulling us down. What if we'd never been out of this room and we just have a basic knowledge of physics? We could repeat the process by having this room accelerate upwards at 10 meters per second per second. If it's accelerating upwards, we feel like we're being pulled downwards. Now really what that is some people call it centrifugal force. Well, that particular thing is a pseudo force. You feel it, but it's not real. It's because, and this is a key term, you're in an accelerating reference frame. This frame that we're in right now isn't accelerating much. It's kind of at rest. Now granted, when you really think about it, there is no true laboratory frame, because the Oxford is on the planet Earth, which is rotating. The Earth is rotating around the sun. The sun is rotating around the galaxy. The galaxy is rotating around the other galaxies. It gets big. So nothing is truly at rest, but in physics, we like to simplify things and say, this is the rest frame, Newton's laws are applicable. In circular motion, it has to follow physics, because that object is rotating, it's accelerating. That acceleration is related to v squared over r. If you're thinking about it as a centrifugal force, a fake force, you just say, oh, there's a force pulling down on me like gravity, and it's related to v squared over r. When you're doing something like this, where it's rotating, we know about translational equilibrium. Equilibrium. All right. And the sum of the forces is equal to 0. If we're in a situation where we've got an object that's rotating, where the radius is a constant, the sum of these forces should add up to be ma. And a is v squared over r. That the forces that we get should end up like that. So in these tutorials that we're going to do tomorrow, we're going to be talking about rotational motion and how it all works together with summing forces. In this, where do I need to go next? There are a few other identities that we need to talk about. This rotation, and when I'm talking about right now, I'm saying that alpha is equal to 0. There is no angular acceleration. Omega is constant. And you may say, but if it's moving, it does accelerate because a is equal to v squared over r, and it's moving, so a must not equal 0. What's the flaw in the logic in this paragraph?
That's where I was going at, sorry.
There's the radial acceleration, the linear acceleration, and then there's the angular acceleration. Linear acceleration just means if you've got something rotating, those points are accelerating inward. Angular acceleration means if this thing is rotating constantly or not moving at all, there is no angular acceleration. But if the object is spinning up or spinning down, as I would say, spinning up would be rotating more quickly with every turn. Spinning down would be decelerating with every turn. And really, it just comes down to A is radial acceleration, alpha is angular acceleration. they are different quantities. So you need to understand that A and alpha are different. One is the first letter of the Greek alphabet, the other one is the first letter to the Roman alphabet, but they are different. With this rotation, some new terms. Okay. There's some new terms that we also need to talk about. Period and frequency. Period is the time that it takes for one revolution, and frequency is the number of oscillations, or more importantly, the better word, rotations per second. So if period is known as capital T, frequency is lowercase f, the relationship between the two is that period is the inverse of frequency. Period has units of seconds. F has units of hertz. 1 hertz, not S, Z, is equal to 1 inverse second. And so that's the relationship between period and frequency. If a disk rotates 30 times in 10 seconds, the period is little t divided by n, where little t is the total time and n is the number of rotations. So if a disk rotates 30 times in 10 seconds, the period is 10 divided by 30, or 1/3 second. And the frequency, which is the inverse of period, is 1/3 inverted, or 3 hertz. So that's a very simple example of using frequency and period. Let's do an example. From rest, an object, not object, object has an angular acceleration of 0.2 radians per second per second. What? Oh, wait. this continues for 20 seconds. After the 20 seconds, it just rotates at a constant rate because it has no angular acceleration. After that, alpha is equal to 0. So really what this thing is doing is it's spinning up at a rate of 0.2 radians per second for 20 seconds. After it's spun up for 20 seconds, the acceleration stops and it's just allowed to spin. So questions. In these 20 seconds, how many times did it rotate? Next, after 20 seconds, what is frequency, period, angular velocity? So after the 20 seconds, what is its angular velocity? What is its frequency? What is its period? And during the 20 seconds, how many times did it rotate? So much like a one-dimensional motion problem, you write down the equation of motion for position in a rotation environment, theta equals theta naught plus omega naught t plus 1/2 alpha t squared. You know that theta naught is always 0. We talked about that. It started at rest, so omega naught is 0. We know that for theta, we talked about it earlier this week, that 2 pi n is equal to theta. If you make one rotation, the rotation is 2 pi radians. If you make two rotations, it's 4 pi radians. So this simplifies to 2 pi n equals 1/2 alpha t squared. In this particular setup, we ask again the question, do we know what n is? No, we're looking for that. Do we know what alpha is? Yes, 0.2. Do we know what t is? Yes, 20. Those were given. So we can solve for n. N is 1/4 pi alpha t squared. 1/4 pi alpha 0.2 t 20. $20 squared is 400. 400 divided by 4 is 100. 100 times 0.2 is 20. 20 divided by pi is 6.37 times. Not very many times, but I mean, that's just the problem. Now that we know how many rotations it did, we look at the other equation of motion. Omega equals omega naught plus alpha t. Again, from rest, 0. Omega is the final angular velocity. Alpha, 0.2 time, not 6.37, time is 20. And so omega is 4 radians per second. Now that we have omega, we got to find period and frequency. That requires an equation, and that equation is 2 pi f is equal to omega. That is how one converts from angular velocity to frequency and back again. Now, a lot of times when I was a student, I'm supposed to sit here and go, I don't remember why 4 pi or 2 pi f is omega. What's a way that you can kind of wrap your head around it? Well, how I think about it, because I get confused occasionally between, is it 2 pi f equals omega or 2 pi omega equals f? If you have one object that rotates once per second, what's its frequency? 1, exactly. What's 2 pi times 1? 2 pi. So if you have a frequency of 1, it's making a rotation of 2 pi radians per second. So 2 pi should be multiplied by 1 because 1 rotation per second is 2 pi radians per second. A frequency of 1 hertz is a period of 1 second. A frequency of 1 hertz is also 2 pi radians per second. So it's 2 pi times frequency to get omega, not 2 pi times omega to get frequency. The conversion that you can also use is frequency is omega divided by 2 pi. So we're going from frequency to omega multiplied by 2 pi to go from omega to frequency divide by 2 pi. Well, in that case, omega, or I'm sorry, we got omega. Frequency is omega over 2 pi. Omega is 4. So this is 2 divided by pi. And the frequency is 0.64 hertz. So it's not turning very quickly at towards the end. And then to get the period, you just take the inverse of frequency and you get 1.57 seconds. And so that's a basic angular acceleration problem. Now, we could sit here and explore this type of problem. And in fact, this type of problem falls into a category of problems I don't really have a title for it, but the most famous, well, famous in my class, but the most used problem is the Fisher-Fury problem. The Fisher-Fury problem was originally designed for a Physics 213 test about 5 years ago. I gave it to the class. The class promptly crashed down onto the floor crying, saying it was impossible. And I'm like, dude, it's not that bad. What the Fisher-Fury problem is it's a lot like this. Now, this problem is a little bit different because it does have a region where alpha is non-zero and then it becomes non-zero. This is a rare, problems on tests and problem sets that deal with rotation fall into two categories. One where alpha is 0 and always equal to 0, or alpha is not equal to 0 and constant. So in one case there is an angular acceleration, in the other case there isn't. The Fisher-Fury problem falls into the case of alpha equals 0. Alpha not equaling to 0, we'll get to that later. It's not in this particular problem set. We'll probably get to it next week. So we're going to initially study this. This is kind of a mutant. We don't deal with it much because I like to keep things consistent. If you talk to any 213 student of mine and you go, tell me about the Fisher-Fury, and they go, he never taught that, they're not an Eschenberg student. The Fisher-Fury problem is mine. So the Fisher-Fury, it starts out fairly simple. You have the rebel rod and reel, where you have the rebel rod and reel has 100 meters of line. You cast out 6 meters of line because you plan on catching the Fisher-Fury. Fisher-Fury. So the Fisher-Fury takes the line. And what's really interesting that up until last year, when people ask the question, why is the fish so furious? My answer would be, I don't know. It's just a furious fish. It's just angry. One individual put 2 and 2 together and gave the real reason as to why the fish is so furious. This will be made apparent in about 5 weeks. There's a particular problem that I do where you figure out that's the fish that becomes the Fisher-Fury. I don't torture. We'll get to that later. You cast out 6 meters of line, the Fisher-Fury catches the bait, and he moves, he or she, we never really determined if it's the Fisher-Fury is male or female. But the velocity of that fish is, it doesn't really matter, you just pick a number, 12 meters per second. And A is 0. This is the linear acceleration. The rebel rod or rebel reel is a 200-gram disc, a solid disc. Now, normally for true fishing reels, it's kind of all the mass is on the edge, but this, work with me here. I'm building my own rod and reel, and I want a solid reel. Question: how long does it take for the line to run out? During this motion, I want AR, I want alpha, I want omega. Really what happens, it grabs the fish and then the disc is immediately at its rotation. Give me period, number of rotations, period, frequency, give me moment of inertia, give me angular momentum. Question? Okay. What else can I ask? What?
I said you bad out of options.
I think I am. I think I exhausted all the letters of the alphabet. Now, with something like this, and this is the problem that I gave them, they all just freaked out. They all just lost their minds. But remember, this is a problem where you sit there and go, well, this thing's moving at 12 meters per second. It starts at 6, it ends at 10. Oh, here's another number that I didn't get, the total time. So I could get the total time before the thing runs out. It's a one-dimensional problem. X equals x naught plus v naught t. It doesn't have a linear acceleration, so there's no 1/2 at squared. The x naught is 6, the x is 100, so x minus x naught is v naught t, so x minus x naught divided by v naught is equal to t. This means that 100 minus 6 divided by 12 is the time. 94 divided by 12, 7.83 seconds. So that's one of the first answers that you got. It's like a Sudoku puzzle. You look for the easiest part of the problem. The easiest part is, well, how long does it take before the line runs out? The next thing that I would attack is alpha. Is the value of alpha 0 or non-zero? So this thing will be spinning up or spinning down. And actually, it's the wrong answer. Alpha is 0 in this case. Let's talk about this. What is the relationship between velocity and angular velocity? V is omega r. Well, what's A? Well, that's dv over dt. And what's alpha? D omega dt. So you can rewrite this as saying dv dt is equal to d omega dt times r. If dv dt is 0, the change in horizontal velocity is 0. The fish doesn't accelerate or decelerate. It's the fish of fury. It just moves at a constant 12 meters per second. Why? Because I say so. I could put in an acceleration, but that would just fry people's brains. If dv dt is 0, d omega dt is equal to 0. And since d omega dt is equal to alpha, alpha is equal to 0 as well. There is no angular acceleration. Now the thing's rotating, that's for sure, because it's pulling string off the rebel rod and reel. And just to make things easy, the line used in this experiment has no mass. It's made out of a special, because the mass, I don't want the mass of the wheel to change because we're about to get to that part. Angular velocity is 0. Does that mean radial acceleration is 0? Non-rhetorical? Real question? if alpha is 0 and this thing is rotating, I just asked this question a couple minutes ago. Is there a radial acceleration? Yes. That radial acceleration is v squared over r. Oh, one of the things I do need to give is what is the radius of the rebel rod and reel? It is 5 centimeters. So V is 12, R is 0.05. So the radial acceleration is going to be big. 2880 meters per second squared. That's a big number. In fact, if one of the things that I do use as a unit is 1 G, that's a horrible G, 1 G, or sometimes I write it looks like a gram, but really, if I write it like that, then G. 1 G is equal to 10 meters per second squared. Because, why do I bring this up? Because one of my few claims to fame is I actually saw Top Gun in the movie theater on opening night. And what's the one thing that they talked about? Oh, so I'm doing this inverted 5G turn. Well, really what they're saying is that the acceleration of the plane is in a circular motion, and their v squared over r is equal to, for a 5G turn, their acceleration is 50 meters per second per second. So when they say a 10G turn, they're talking about 100 meters per second per second. Now, for you and me, for normal humans, 1G is fine. We live in that all the time. If you're in a 3 or 4G environment, that means you feel like you weigh 4 times as much. People start blacking out at 4 to 5, depending on the situation. Because at 4 to 5 Gs, the heart doesn't have the strength to pump the blood up into your brain. That's why if you're doing like high G turns, you try to lie down and stay on a level surface so the brain doesn't get overwhelmed by blood or be drained by it. And then 10 is where we're talking about, like, I think pilots who are doing those high G turns wear special pants. And those pants, what do? They squeeze when they're doing those high G turns. Why? Because it's trying to keep the blood up in your brain. At 10 to 12 Gs, the pants just go, I give up. And then blackout and death follows. So for this, we're talking about 288 Gs, which for a human is quite lethal and would be quick and painless. You would turn into goo, probably. And this is one of the main advantages that it's a bad, good film, or it's a good, bad film. Skyline, when the aliens attack, and they basically capture the planet because they got the bug light that turns humans into just dummies. But they were attacked, one of their motherships was attacked by basically just a squadron of drones. And these drones had the advantage of the alien ships had, well, basically the aliens were here for our brains to pilot their ships. So the brains were in the planes, and they would do these 10G turns, but they had to have special technology. Well, of course, they came from another planet, so they do have it. But for the drones are just mechanical. They're controlled by a pilot. Drones, missiles, all that stuff, if it doesn't have a human in it, 10 Gs is no problem. 50 Gs is no problem. You could spin those things all sorts of ways. And now it's just a limitation of the engineering of the material. Humans are quite soft and squishy and destroyable. And so that's why I think future generations of jet planes will not have humans in them. They will be piloted by humans remotely, because a plane that's capable of a 50 G turn has a natural advantage over a plane that can only turn 4 Gs or 5 Gs or something like that. It's a very substantial advantage. But that's the story behind, well, what's a G? It's literally a unit of 10 meters per second, or 1 gravity of acceleration. So that thing is spinning around at 288 Gs. Well, what is the omega? The V equals omega R, or omega is V over R. The V is the linear motion of the fish, 12. The R, 0.05. So the omega is 240 radians per second. Or if you want to be incredibly exact about it, 240 inverse seconds. Just as a side note, angular velocity is frequently, no pun intended, called angular frequency. Because radians per second is simply an inverse second. What is a frequency? A hertz, units of hertz, inverse seconds. And so the units of angular velocity are the same technically as frequency. That's one of the other reasons why I tend to use radians per second when it comes to omega, because I sometimes get it confused with frequency, which is in hertz. So now that I have omega, let's get frequency. Frequency is omega over 2 pi. Well, omega is 240. 240 divided by 2 pi is 120 over pi, or 38.2 hertz. The period is inverse frequency, so 38.2 inverted, which will be 26.2 milliseconds, or 22.62 times 10 to the negative 2 seconds. I would accept either one. So what this is, the Fish of Fury problem, is just a rapid fire problem. Boom, 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 boom. It's not as involved as a 2D motion problem in terms of you've got to set it up and do a lot of problem solving. What it does is it tests your ability to recall different rotational quantities and manipulate them appropriately. We have T, radial acceleration, alpha, omega. Did we figure out N? Not yet. Period, frequency, and then moment of inertia and angular momentum. To get in really quick, we could do it a lot of different ways. The easiest straightforward way is N is the distance linear. It can be expressed as this, divided by the circumference. The distance in this case was 100 minus 6, or 94 meters. The circumference is 2 pi r. Circumference of a circle, or 2 pi r, will not be in the equation list. You are a human. You should know what the circumference of a circle is, just like you should know what an area of a circle is, because you're an adult. So this is 2 pi 0.05. So this is 94 divided by something. $299.2 times. And what's really interesting is that you could get frequency by, frequency is the total time divided by the number of oscillations. The total time is 7.83. No, that's not F, that's period. The total time divided by the number of rotations and you get 26.2 milliseconds.
So we could use that on.
Yeah, you could find period this way. You could find period that way. There are multiple ways to get to the same answer.
We could use that to find the end too.
Yeah. Yeah. In a problem like this, it's one of the lessons that I use the Fisher-Fury problem for is it is frustrating for a student to see a problem where there are many paths to get to the same answer. It frustrates them. And I want them to get over that. One of the ways that I encourage them to get over that is that their frustration only makes me happier and stronger. So, show me wrong. Learn how to do it the right way. And by right, be content with there are many different ways to do this. There are certain things where I go, this is pretty strict on how we do it. Vector addition is one. If you take 214, there's a particular problem called the Kirchhoff's law problem. That I'm very passionate about you following a set procedure. But for something like this, you can kind of, as one of my students said, you could freestyle it. You just kind of meander through the problem and it works out. Let's look at the list. Oh, I and L. Moment of inertia of a disk is 1/2 mr squared. M was 200 grams, I think, of the disk. Yeah. 0.2. The radius was 0.05 squared. And so this makes it 0.1 times 0.05 squared. 2.5 times 10 to the negative 4 kilograms meters squared. Those are the units of moment of inertia. M gets switched to kilograms, R gets switched to meters per second. And that gives you I. The last bit, angular velocity by definition, is I omega. Well, I is 2.5 times 10 to the negative 4. And then omega is 240. So this gives you an angular momentum of 0.06 kilograms meters squared per second. And those are the units for angular momentum. Oh, another letter that we could use. E rotational. What is the kinetic energy of the wheel as it's moving? Well, what's kinetic energy? 1/2 I omega squared. Now, all of these equations will be listed on your equation sheet, with the exception of circumference. But all of these will be on it. It's your ability to recognize that I is moment of inertia, L is angular momentum, KE is kinetic energy. So this becomes 1/2 2.5 times 10 to the negative 4. Omega is 240 squared. And that gives you 7.2. Now, the unit that gets kicked out of this, moment of inertia I, kilograms meters squared. Omega squared has the units of 1/seconds squared. Readjust these things. It becomes kilograms meters per second squared times meters. What's a kilogram meter per second per second? It's a Newton. Newton meter. And what is a Newton meter? A joule. So the unit is 7.2 joules. And so what this is, understanding the Fisher-Fury problem gives you a very firm understanding of rotational motion. In the test, and this is one of those things, we've got 7 minutes, I'm only going to use one, just so that because I can hear people packing. On the test, you're either going to get a problem where alpha is 0, or you're going to get a problem where alpha isn't 0 but constant. The one that's done on the test won't be on the final. The one that isn't on the test will be on the final. We will go over the alpha is non-zero problems next week. And that is it. Tutorial tomorrow here, 1 o'clock.